So it's finally time that we introduce our own talk. Now, let me put this in full screen. Okay. So, you may have guessed it. So I'm Daniel, this is Jiska, and we will talk about Fitbit firmware hacking. So this work was done in our secure mobile networking lab. That's a department of the University in Darmstadt in Germany. And yeah, so let's dive into it. A short motivation. So there was already an article on the Telegraph about our work, and especially this comment catch my eye. So it says, "Dear hackers, please update my Fitbit to show that I can run 10K every day this week." And we wanted to help this poor guy, obviously, and to achieve his goal. And yeah, we just found this funny, but it's also encouraging. And apart from this, bit more earnest, I guess, is that insurance companies now grant bonuses in case you wear Fitbits and can basically show them that you are actually, walk, I guess, or be healthy in general. So then Jiska will tell you something about the communication.
So in a Fitbit system, you will always have a tracker and a server, and the tracker is sending fitness data to the server, which is end-to-end encrypted with a symmetric key. And these keys are rolled out in factory. So when you get a tracker, the key is already on it and it's unique. The tracker itself is limited in power, so it just has Bluetooth LE, which is not further secured, but it doesn't really matter because the end-to-end encryption is still there, and the app is then forwarding this traffic towards the server with HTTPS. Now, the problem is that this end-to-end encryption is only available in recent trackers. So starting from 2015, it was mandatory, but if you get an older tracker, it might still not encrypt. And even worse, there has been another vulnerability which just enabled memory readout from the tracker via the app. So you can bypass parts of this encryption. Looking a bit deeper into the system, the tracker is recording activity of Susie or whoever is using it for roughly a week. And after this week is over, the memory is full, and then all old activity is withdrawn. So you need to synchronize it with a server, again via the app. Normally, this should happen each 16 minutes if you're active. And there is a megadump being sent to the server. The server is then decrypting this megadump, storing things in the database, and answering with a megadump response, which also contains user settings. So the user has a certain stride length, might have alarms in the morning, and so on, which is all set in the response. And the tracker itself is not having a display often, and so you cannot really see what is happening, but you can see your data in the app. And this is done via JSON over HTTPS directly from this activity database. So you can kind of guess like what was uploaded and what was updated since the last upload. Now, another important thing is that only a person owning a tracker can actually read this data from the server. And for this, the user initially logs into the app and does a local pairing, which is Bluetooth LE pairing without any pin or something. And then there is a remote association where the user actually is copying a pin, but this is proprietary. And then in return, the server gives you some authentication credentials. So this process you only do once in the beginning, and then you have authentication credentials. And with those, you can actually then do some special commands, like there's a live mode where you can get plain text data summaries of the current day, or this memory readout. And These authentication credentials are reusable even if you associate it to a new user and so on. So you can reuse that forever, no matter what happens. So next, Daniel is going to tell you how to find more about the inner things of this Fitbit.
Okay. So first of all, we look at our tagger model. We have our Susie Fit, and of course she uses the tracker, and which is, as we learned already, uses a symmetric key to encrypt her data, also stored in the tracker. And but now the question remains: what happens if Susie has some malicious intents and basically maybe wants to modify the data which is stored on her tracker? Or she wants to get the encryption keys to basically decrypt her data offline. And for this, we looked into the hardware a bit, and this is a high-level overview, I guess. What the Fitbit Flex consists of. And so we have our main system on a chip. We have a BLE chip, of course, which is needed for the communication with the smartphone. And we have an accelerometer which traces your steps basically, or gives this back sensor data for your steps. The firmware itself, we already got some hints which software they used for their firmware. And so for encryption, they used the libtomcrypt. And for BLE, they use some library which at least has very similar, or which is really similar to the libBLE shield. So this really helped us in the reverse engineering, of course, so you can map functions and so on and name them. So this is how the PCB looks like. So in this screenshot, I fix it somehow screwed up, and the left part is a bit damaged, but it's not so important.
It happens when you pull it out, so you need a hot fan, and then you need to pull on the LEDs, and it sometimes breaks. But it doesn't matter, it's still functioning if the LEDs are off.
Yeah. Okay, so what we want to do, of course, is to connect the debugger to it. And for this, we use the SWD protocol. So this means we need 3 pins and ground. And so I highlighted them here. So you might ask yourself, how do you identify these ports? Of course, you basically need to damage one Fitbit Flex and desolder its chip, and then look up the pins which are used for the BGP array for JTAG or SWD in this case, and then you just basically try out each and every pin and look where it comes out on the BGP array. And so we identified these 4 pins, and on the right-hand side there you can use these connectors here. Can you see this? No. Like this. Yeah. So these two connectors to power up basically the thing. So this is how our setup looked like here on the right-hand side. It's a bit crude, but it worked for us. Right, and with this we were already able to dump the firmware. And so it basically consists of 3 main parts. So the flash, which contains the firmware code, an EEPROM, which contains information that should survive an empty battery, and an SRAM for firmware variables. It's also no problem in case you damage or break your Fitbit Flex in this process, because they are cheap as hell. So one currently costs $1 or $2 on eBay, broken ones of course, but we do not care if the battery works or not. We just basically remove the PCB from its casing and tag it to a breadboard and desolder the battery anyway.
And like a third of them had battery life still left for a day, so if you don't want to open it and just modify the firmware, which you show later, it also works.
Okay, Yeah, and some of our Fitbit Flex, the magic smoke escaped. So, but yeah, we have some in spare. Right. So the flash content looks like this. There are basically two parallel or two operating systems which can't run in parallel, but there's basically a backup for each other. One is called app, and the other one is called BSL. Basically, app is the BSL, just with more functions, and yeah, they use it for the firmware update, so to always have one system which actually works. And apart from the flash, there was also this EEPROM section, and this contains the serial number, an encryption key, and an encryption switch, and also your fitness data. So basically, also everything you need to decrypt your data if you want. So I think this is something we can all agree on, that it is important for a reverse engineer to get our tool set straight. So what we want to do is to enable GDB access. So we already hooked up the PCB to a debugger, but when I tried to do debugging, the problem was it connected after reset, but in case I hit continue, it disconnects. So what basically happened is that at some point in time during the firmware execution, the GPIO ports get not disabled, but used for something else. And so I just asked myself, yeah, well, let's just reset them. I do not care what they do otherwise. I want GDB access. So for this, we used a framework which we developed also in our department at the university. So initially, this framework was developed to patch, to binary patch Wi-Fi firmware, for example, on the Nexmon 5 smartphone. And we adapted this to patch our Fitbit firmware. And yeah, with this, we should be able to re-enable GDB. So this is basically how this mess looked like. Oh, there's something missing. Yeah, well, okay. So basically, on top of the initialization, I know that debugging worked, but in the end, it didn't. And somewhere in between, I don't know what happens, and I don't care. So I just want to re-enable the GPIO ports, and for this, in the end, I just basically oh, there's the icon. So in the end, I just ended up with, after initialization, I reset all GPIO ports, and with this, I was able to reconnect my debugger. Problem is, of course, this does not come without side effects. I have no idea what they are really used for. So what we can also do is introduce a new Bluetooth command, which we can just send to the Fitbit, and then the Fitbit will re-enable the GPIO ports for debugging. So then Jiska will tell you more about the firmware flashing process.
So in the first part, we mainly analyzed the hardware and flashed with the SDM tools, but it's much cooler if you can just buy any Fitbit and then flash it without opening it. And for this, we look deeper into the update process. So if you synchronize with these mega dumps and these activity records, there's always the firmware version included, which means that also the application and the server know the version running on the tracker. And the server will tell to the app if there's a new firmware update available. Still, the user needs to start this update. So the user needs to ensure the battery is full, the tracker is nearby, because this process takes like 10 minutes and it should not be interrupted. And as soon as the user starts it, the tracker will again send its version, and the smartphone application will forward this version info with the firmware requests, and in response send these two firmware parts, the BSL and the app. And first the app is running, and the BSL is being flashed from the app, which means it's first validated, then written to flash, and then there's a reboot to BSL, and then again from the app there is the BSL being flashed, and then there's a reboot again to the app. So you have this double update, and I mean, you could so they ensure that everything is running by having two systems, and you need to be able to boot into one of the systems and so on. But if they would trust themselves a bit more, then the firmware update could be a bit faster. Anyway, so they just do a full firmware update, and that's why it takes 10 minutes. Now this looks pretty simple, but actually flashing something onto a tracker is not that simple because they do a bit more stuff around it. So the main problem was that they use encryption. So if you buy a tracker on eBay, currently they have encryption enabled. They still did not get the fix from October 2017, so you can still read out the key from memory, but you need to do proper encryption. And we found out that the trackers use XT mode, and if you look into the source code, you will see XT has a certain 8-byte string that you can localize, so there's no other strings in this part of the encryption, but you know this 8-byte string, and then you look out there for ARM libraries having XT, and then there's like 2 or 3 libraries, and the one that matched was libtomcrypt. And with this, we found out all the functions. So they have a 2-byte nonce, the encryption key, and an authentication MAC. And if you apply all this properly to the firmware, you can actually flash the firmware. You still need to do some byte flips and so on, but that's pretty simple compared to this encryption. And now we even built a complete framework that lets you do those things. So first you get the key from the tracker with memory readout, with our own app that we have public on GitHub. And if you want to build your own firmware image, you can also extract the firmware image with the memory readout. Then you can copy the firmware to your PC, run the Nexmon framework, make whatever patch you want, and copy the firmware back. And then you can do with our smartphone app this complete flashing of your own firmware. Or if you have someone who gives you a precompiled image, which already does fancy stuff, you can also just get this image and do everything in the smartphone app. And as a first demo, we tried to override the steps function. So there's a get steps function, and we just return steps by 100, so you can see that the steps are increased in multiple of 100.
Keep in mind, this is the original Fitbit app and original, I guess, Fitbit Flex.
Yeah, it's not disassembled, teardown or something. It's just closed, yeah. And I just detected, so if I reset the flex with this configuration, something funny happens because the steps are then multiplied by whatever, 1,000 and so on, and then I can reboot the flex a few times, so it has a button to reboot, and then you get strange figures like this one. So, and you might think I got blocked for this, but my account is still working, so I don't know. So they claimed they have some detection for this, but whatever. So you can be very sportsy if you're a hacker. But despite this, we also wanted to try to make a bit more usage out of this. So I mean, the flex, it's super tiny, and you can maybe build something more. And we tried to access the accelerometer. And there is a help function, so that's actually the only function containing some strings. And the help function is used in during factory, I guess. So it's only having references to the hardware-related things, and there's also the accelerometer having the last XYZ values, which are 2 bytes each. And we digged a bit deeper into this, and we found the configuration register, which shows a configuration of 100 Hertz. You need something like 25 Hertz to figure out like what are gestures and things, so that you can actually interpret some movements. And we thought, well, maybe the Bluetooth LE connection is fast enough for this to extract something that you can actually interpret movements. So what we did there is this live mode that you normally use to display this activity data. And normally it's just updated if you have a new value. So for example, if you're running and you get 10 new steps recorded, then in live mode you get the next package. But we actually try to get the maximum update rate out of this function and copy the accelerometer values to this. And to ensure backward compatibility with the original app, we also introduced a special second command. So you send a command to the tracker, say, I want now the accelerometer data and so on, and then you get this. And we measured it, and it's above 66 Hertz, so it's enough to interpret movements. And you can use this, for example, to first develop something like in your own smartphone app or with Python or whatever if you have Bluetooth, and interpret those movements. And later on, if you want to have the same battery performance, so because if you have the tracker and you transmit all the accelerometer data live all the time, it's of course draining battery. But as soon as you have your logic implemented, you can use our Nexmon framework, implement some C functions doing the same logic, flash this to the tracker, and have your movement interpretation at the same low battery usage. So the hackable versions which have the memory readout which is required are the Fitbit 1 and Flex. So at least when you buy them, they typically don't have the patch. So we bought some and none of them had the patch from October. There is also memory readout in the Charge HR, but that one was fixed before. So probably it's harder to get one of these somewhere in a store.
Yep. Okay. Also keep in mind that these accelerometer data are raw data, so they are much more accurate than anything you get with the default firmware. Okay, yeah, to sum this up, our current project status is that the Fitbit security team is very responsive and do a good job in terms of the responsible disclosure. We can write them emails with PGP, which is not, which is something we can, which we find good, and of course they are very professional. And also, what we do is we send them early versions of our publications before we hand them in. Okay. And so our current tools basically are all open source. They let you let you do some server independent actions, such as the live mode we discussed, or the memory extraction, and also you can do the firmware flashing and patching with the Nexmon framework. Okay. So in summary, you can go out and flash your neighbor's devices. You can also keep control of your own data and run any code on your Fitbit. So that's it from our side. And I guess we can now do some Q&A. But we still need to figure out how to hand out the microphones. Oh, okay, there's one right there.
Maybe I just completely missed this slide, but were you able to extract the firmware encryption key, because it's specific to each device, correct? Wirelessly, or did you need actual soldering to a debug port or EEPROM to extract that before modifying the firmware?
Yeah, so wirelessly works actually with these models before October 2017, or if they were not patched, which seems to be the case, so at least for the ones we bought this way. So if you buy one and you don't update it, you can do this with the memory readout, and the soldering still works with the most current firmware. So if you open it, you can always access it.
Yeah. So this is basically, so this memory readout command is basically, I guess, a leftover from development process. Okay. No more questions? Then thanks to Hugo for allowing us to basically hot patch the schedule. And yeah, thank the speakers again.